So I would like to introduce that next speaker from that wonderful speaker from the United States. So Professor E. Guo is the Thomas Hartrick Chair Professor at the Department of Electrical Computer Engineering at Stevens Institute of Technology. So please.
Thank you, Kenji. Thank you for the committee to invite me. I'm honored to speak here. My first equal paper was in 2002, when I was doing my postdoc at Oak Ridge National Lab with Dr. Lynn Parker. I was working on multi-robot motion planning at that time. So 22 years passed, there has been a lot of progress in the field. But are we seeing many robots in real-world settings? Maybe not. So why? I'd like to offer some lessons we learned for the past decade. So robots are made for applications. When we put robots in the real-world environments, that environment is many times dynamic, it's cluttered, and uncertain. So we need the robots to deliver pizzas, to cook in the kitchen, to work side by side with human workers in factories, at construction site. We know the challenges include that many times the pipeline design or perception, planning, and control, and uncertainties in each module were built up. Also, the pipeline design caused latencies so that the actions are not fast enough to respond to the dynamic sensing input. So I would argue that the key issue is the interaction between the robot and their operating environments. So I'll offer some lessons we learned through the research projects my research group have conducted during the past 10 years. In 2010, you may recall that there's a Deepwater Horizon disaster occurred at Gulf of Mexico in US. A large amount of oil spilled and caused the largest environmental disaster in the history. So right after that, there has been some research on cleanup mission. My group was lucky to get a US National Science Foundation sponsored project to use ocean robots for pollution plume monitoring. So we proposed to develop the dynamic plume tracking using the unmanned surface vehicles. When I first looked at the problem, from the controls background, I was thinking, okay, we have mechanical systems. I can model it, control it. And we have the water source dispersed in the water. So it's a physics phenomenon. I can use the ocean chemical the modeling to model the evaporation diffusion process of the source dispersed in water. So that's a partial differential equation we start with to model the spatial temporal process of the concentration C at the position X at the time T. And we developed multi-robot tracking control with a constraint of nearest neighbor communications. So with that's, I'm not going through the model, but the basic idea is to use the sensors measured and establish observer, and then use estimated plume front to control the robot to track the plume front. We did a MATLAB simulations, which works well. We added uncertainties here and there to account for the uncertainties that we expected in real-world environment. And then we bring our algorithm to Hawaii in 2015. I collaborate with Dr. Bingham at University of Hawaii, and we did a test at the Mackay Research Pair in Oahu, Hawaii. So we set up the short stations. Students did heavy liftings. And we deployed plume source using the rotamine dye, which is a pink chemicals. It's environmental friendly, and it's visible, so we can track, we can see the performance. We assembled the surface vehicle, launch it. And students did a lot of troubleshooting on the vehicles, on the electronics, on the water. And we even deployed a balloon to have a camera, so get some view from above. So it comes testing. We could test the vehicles and algorithm in a few days in a row for 2 weeks. I'm not going to finish this video. So here are the lessons we learned. So in real marine environment, first, the measurements are never smooth. So on the right bottom, you'll see that's a concentration measurement by the sensors. We could do the leader-follower control for 2 surface vehicles. We could do the level curve tracking to a certain degree. However, the dynamic plume front tracking is hard. The challenges are mainly from 2 aspects. The first is environment uncertainties. Due to the temperature changes and the wind direction changes, we see the chemical plumes that change directions every 20 minutes. Even in the morning and in the afternoon, the plume structure can be very different. Also, when we deploy the sizable surface vehicle in the water, it disturbed the plume structures. We learned a lot from the real-world experiments. Later on, my group have several projects to deploy robots in human environments. The first one is to have a robot to interact with pedestrian flows. So the robot is deployed to try to slow down one branch of the pedestrian flows so that the merging area, which is a bottleneck, the density does not build up to cause cross stampedes, disasters. The second project, we try to understand the pedestrian dynamics so that we can have a robot navigate in crowded environment without freezing. And third project, we developed the integrated robot and wearable sensor system to monitor the gait and assess balance in the older adults' walking exercises. I don't have too much time, but we know that in humans' motion, are kind of random. Humans change their minds constantly, change their behaviors. So we didn't tend to model the human motion, but we use an input-output point of view. We use a sensor to measure the collective pedestrian dynamics and the human-robot interaction. and use that to control the speed of the robot. We formulate it as optimization problem, and developed adaptive dynamic programming-based learning algorithm to learn the optimized robot moving speed so that the collective pedestrian flow reach a desired optimal level based on the capacity. So let me conclude here. So model-based method rely on the physical model of the robot and its operating environment. Learning-based control use neural networks to map the input-output relationship and the dynamic evolution of the relationship. It relies on data generated by the robot while interacting with the environment. So currently, my group has been focused on the intersection of these two types of methods. There has been a lot of good work on this aspect. Many good works appears, such as rescue learning, assistant learning, or in controls field, there are certified safety and robust tracking. Yeah, my group has been working to use the data-based method, have better estimate on the residues on uncertainties where we deploy the robot in real-world environments. So that concludes my talk. Thank you very much.
Thank you, Yi, for giving a wonderful talk about robot control, also natural environment. So any questions? And from now, if you have a question, please stand up. Then I think a little bit more visible than before. So raise hand and stand up, please. Any questions? There? OK, thank you. So over there.
Okay.
Hi, Professor. Thank you for the talk. My question is, some of the corner cases that we encounter in pedestrian flows, how do you tackle them? Like, do you use the model-based approach or the learning-based approaches for that?
Learning-based approach. So in the when you deploy robots in human environment, we didn't try to model it. We did simulations using the social force model, and we try to match with real pedestrian flow. Only qualitatively it matches, quantitatively it doesn't match. So for the pedestrians database method, and you can use real measurement, right, like input-output relationship to map. Using neural network, I think database method is a better way to go.
So thank you again. Thank you, Yi.
Thank you.